Okay, so we're going to start. Hi, everyone. My name is Blum, and I'm a big data architect for Verint Systems. And in this talk, I will tell you about a journey that we had. You know, we use the word journey a lot in these places, but it has been a real journey when we transformed our system from a collection system to an analytics system. I'm speaking about a national cyber defense system that we have been developing for many years now, but in the past, like 2 or 3 years, really we have transformed it to the analytics arena. So a few words about myself. As I said, I'm a big data architect. I tweet stuff, so you can follow me there. I've been mostly in the past 15 years working with, big data, like many of us here, before we actually called it big data, but data fusion algorithms and stuff, and cyber, and a lot of IP networks and IP probes and high performance storage. So it all kind of converges to big data eventually, but now it's great that we have actual names for all these things. So what we're actually up against, or it's a bit of motivation to the whole system. So, Googling all these recent events that you see in the media, these are cyber attacks that are performed by nations on nations. So they have their own distinct behavior, and you see all these different attacks, and this is a recent one, this Saudi cyber attack. But it all shares some common factors, and let me just start with a use case. Maybe it will be clearer who are actually the customers. So usually we're talking about nations or about ISPs, internet service providers. So let's say we have a government ISP. This is something that many countries have. It's like a division or a unit that is responsible for all the government agencies and ministries and all their public web pages and services. And they give them all the IT services and network management and, of course, the cyber protection, naturally, and monitor and manage their network. So let's talk about that use case for a second. And to explain that, I know this is like mainly a cyber-themed room here, but how many of you are really acquainted with cyber? Like a quick show of hands. Okay, yes, okay, I love that response. So either you're shy or I don't know, because if many of you don't, so it's good that I've put these slides. What I'm going to do now, we're going to have a very quick cyber crash course. I do believe that these 2 slides summarize everything you need to know about cyber, for this lecture, but so okay, let's look at a corporate network, and just in a basic way, how does it look? Okay, so you have the internet and some sort of a firewall. Behind that, you have a network which is called a demilitarized zone. It has all the outbound services of that organization. The websites, servers, email servers, FTP, etc. Then you'll have another firewall, and behind it, you'll have the real interesting private network. So you have databases and client endpoints, the actual devices, either like I'm surfing with my mobile phone or a laptop, and also, user management, etc. So what I'm going to do now, there is a concept called the cyber kill chain. It's widely known, and I'm going to draw, I'm going to show you the cyber kill chain with an attack on this sample network. It's all high level, but the concepts remain. So let's say we have a malicious agent that wants to infiltrate this network. So first, he would define his goals and targets, and will gather intelligence in very myriad ways. It's a whole theory around every sort of step of the way. But eventually, once this attacker knows what he wants to attack, he or she will create their tools. And it's usually in these cases, these are very distinct tools. This is not like something common. Every tool is different. And it's all based on exploits, on things that are still unknown usually as weaknesses in the network. And then they will infiltrate. So for instance, a good example is an email, either a targeted email to a person in the organization or like sending to many people, and one of them will have to click that really interesting link that obviously downloads malware or whatever other malicious thing that will get this agent inside the network. So now the agent is inside, and well, it's some, I don't know, some laptop, some device, some server. It's not, it doesn't have to be the actual goal of the attack. So now there's a step that is called the call home. Now he will contact a command and control server or a group of servers or a hierarchy of servers. But this step is saying, OK, I'm in. Now what do I do? So usually the next step would be you need to move laterally. You need to move inside the network, go to, I don't know, the CEO's laptop, I don't know, or CFO or whatever. So in that case, let's say I'm going to go into some sort of a database. And now when I'm inside that database, well, this is the, I don't know if it's the fun part or the worst part, but this is the end game. After this step, we have data exfiltration or damage or whatever you would expect to happen in such an attack. So this is a very basic portrayal of an attack, and along with the cyber kill chain. So naturally, we would like to deploy sensors on this network, all sorts of sensors. This is not really a cyber lecture, so let's say these different sensors, they just cover different parts of the cyber kill chain. So once I have all these sensors in place, excellent, I see everything that happens on the network. I have everything I need to, I don't know, monitor and prevent attacks. Well, not really. But just to make the story a bit more complex, this was one organization. Let's say this was some ministry, but our government ISP supports all the government ministries. So you have multiple organizations that are all backhauling their alerts and metadata back to the single center for the cyber protection. So how much data? A lot. Let's say we have 100 gigs network with 100,000 endpoints. This is actually not our largest deployment, but this is a rather big one. So I'm, again, not going to get into the different sensors type. And this is every one of these sensors is great. You can go to other like cyber conferences. But the idea is that it's a lot of events and a lot of storage. And eventually, it scales up to hundreds of thousands of events over, and when you store them over many months, you have trillions of events stored in petabytes of data, and that's what we actually need to remember. So what really makes cyber an interesting case is the fact that these attacks in these special cases are very rare. So we have a thing called alert fatigue, and I'll try to explain in a few bullets how does it happen. I mean, we have a sensor, let's say this is a sensor, that analyzes our TCP connections. And somehow this sensor knows when a TCP connection is a malicious connection. And this is like the best sensor. We don't have such a sensor. It's an amazing sensor that has zero false negatives. No one has such a sensor, but let's assume that you have one of those. And it's such an awesome sensor that only once in every 100,000 connections, it will trigger a false positive. And again, if you have that sensor, buy it, use it, sell it, you make a lot of money. But the idea is that only 1 in 10 million connections, for instance, is actually malicious. So when you make a quick division, you get to walk through 100 false alerts until you find the real one. And when you also don't have many people that actually, like you have a low head count to do that, and watching all those false alerts, you get the alert fatigue. And how do you address that? Well, that's where the multimodal data fusion comes into play. And this is a thing that many are doing, but it's hard to do it right. And it's hard to actually nail it and make it work. Because what you do here is say, OK, attack is a process. And we know that this process has a distinctive trail of evidence. And we know that in all attacks, like the attacks that I've shown you before, the evidence was in the logs. I mean, nothing is a surprise. But still, it was discovered like months after the effect. But we know that we have those events. And we know that each sensor has a partial view. And we know that it has tons of false alerts. So we need to create real incidents by having some sort of statistical correlation of all these different events. And this is actually the game here. This is what most of our work is, to get all this information, which is really easy to gather. Let's say we have all those sensors. Some are good, some are bad. But we have all the information. How do we actually make real information out of it? So just to wrap up about some more limitations, and then we move on to the solution. So let's say this organization, he has first a cyber operator. We have many people using the same system. So OK, for the operator, it's like a information system for him. He looks at the different alerts and maybe sees something interesting, maybe groups a few alerts and send them to the analyst. But he expects the results to be like in a second's delay. Now, our cyber analyst, he's OK with doing like longer aggregative queries over longer time frames, mostly on metadata. So he's OK with like minutes of delay. But when we get the data scientists into this system, they're fine with building a model overnight. They're all right with hours. But this is, again, the same data, the same system. And why it's the same system? Because we have DevOps team that every time we propose to add like another system or another technology, they say, no, no, please don't, please stop. And we have managers that say, you have to keep this a very low footprint. And this is actually a very strong demand that we have in our case, either way, that all our systems are still on-prem. So we want to move to the cloud, but it doesn't happen yet, mostly because of the customer demand for these very unique systems. And this is a very hard constraint for us, and we are willing to pay in other aspects to gain this very low footprint because it's very good maintainability and for the customer eventually that has to maintain this system. So moving on to our solution, very high level architecture of how we did it. We did a full overhaul of the system. All the analytics are based, well, on Hadoop, of course. Spark is our main processing engine. I think I fit into many of the lectures here. We still use Yarn for scheduling. Kubernetes, like Spark on Kubernetes, like from 2.3 seems amazing. We're still in Yarn. Airflow manages all our jobs, and Ambari for managing the cluster. Our messaging hub is Kafka. We're very happy users of Kafka, our largest deployments with millions of events per second, and we're really satisfied. And everything is serialized on Avro. We store all the data, most of it in Parquet, whatever structured data that we can. We have some CSVs, some binary data, but most of it is Parquet on HDFS. And we have like 5 teams working on the actual big data applications that we have developed over this infrastructure. So we have enrichments and correlations, which I will dive a little deeper right away. Also entity analytics that I will explain about that. Graph analytics, our large-scale repository, our rule engine for triggering real-time alerts. And we have a very interesting way to well, you know, most of the data is encrypted, and if we still want for instance, to detect a command and control connection, we have models that know to alert on command and control over encrypted data and other really hard to decipher events. And all of this information also is available for our data scientists that I will explain later, either ours or the customers. And well, all shared on the same tools, same clusters for DevOps, etc. So now I'm going to explain a bit about each of the components as time permits us. So first, enrichments and correlations. I'm going to give a very high level on that flow. We have many components in that flow. We call it the mass flow manager that we have. And one basic example of it, we have all the events coming in Avro over Kafka. We have Spark streaming application to do that. So the first step would be we have something that we just simply call the join enricher. And we want to enrich the data. For instance, I have IPs, and I want to know the geolocation of that IP. Where is that server that I'm communicating with? So it's either static or dynamic. I mean, we have tables that are static, but also we have tables that are updated, like user information that is updated all the time, and we want to know which users serve to which servers, etc. So we take all the events, we extract the fields that we wish to enrich, we put them all in a data frame with the actual Avro message as a blob, and then we just perform left outer join, and we just enrich it, and you get like records of the fields, of the enriched information, and the blob. This is what this enricher does. And then we have an iterative enricher, which goes through all these records and inserts all the different fields that we have enriched into the blob. And also, for each record, we run all sorts of third-party enrichment engines. For instance, we have like a URL, so we have like a library that is third-party that says, is this URL malicious or not, or all sorts of other enrichment engines. And eventually, we have all sorts of correlations. We have different events that we want to not just send as different legs of an event. We want to correlate them and know that they happen simultaneously for some reasons in some of our algorithms. So for that, we used structured streaming. We have like the same ID in different events, so we unify them and just output one event and just throw the others away. We have more correlations over time, like things that happen in the same time, but we don't have IDs. So we have a lot of other stuff going on here, but this is like the main concept. Now this is an interesting thing, the entity analytics. What we do is we have all that network information, but we also want to have understanding of the actual network, not just the packets going through it, actually which entities are in the network. So we have, again, it's Spark streaming, collecting identifiers that we see in the network, and we aggregate how much traffic is for each identifier that we see, recognize patterns, when are the peaks, when are the lows of that server, try to understand what is the role of this server from different sources, like user directory or the actual traffic, and say, okay, this is a sysadmin, this is just a news website that people are contacting, or this is like, I know, a malware command and control server that, if it's well known, it's an easy one, but the problem is that usually we don't know. So after that, we derive anomalies. After we understand what are the behaviors of the network, after we learn the network and we know what is the actual behavior, we will have anomalies. And that's an interesting concept, just to stop around that. We can have suspicious indicators that are very simple to see. Like someone is port scanning the system. Someone is looking for an open port. So it doesn't have anything to do with history. It's just people scanning the ports. OK, that's an alert. But on the other hand, you have suspicious behavior, which is someone is always having a machine working during daytime and downloading 100 kilobytes per day, and suddenly he's sending gigabytes of information to I don't know where, to a server in a specific country that we know they want to attack us. So it's you have the events that are like obvious, and you have the events that you have to derive from behavior. And the way we do the aggregation is we have Spark streaming for every 15 minutes, and then we have batch jobs. Airflow runs our batch jobs. It's kind of complex, direct acyclic graph that we have for hourly aggregation, and daily, and day of month, and hour of day, and day of week, and week of month. So we have all these different compositions that try to explain how is the behavior is over time. So we have Parquet for almost everything. And the reason we did that, first, we had experience with data warehouse, a lot of experience, and it's expensive and not enough analytics in it. And we considered the various like HBase and Cassandra, but eventually we went with Parquet. And for our use case, it was great because, first of all, ingestion is fast. It's like 10 times fast when writing to a Parquet file. We just dump it all in. I'll explain later what else. But also, it has very good scan rate for analytics. It has a great compression. It's the right ones. It's column-based. You don't index like every single record. We have another indexing solution that I will talk about in a minute. But we know that you have slower random access, which is something that we are willing to pay for if we're saving, like instead of saving 10 petabytes of data, we'll save 1 petabyte of data. That's like the main consideration for us. And our users, they understand that they will wait for like a minute for a response or for 5 seconds in other cases, but it will not be a millisecond response time. But we have solved it to a second level response time. And this is our large scale repository. So what we did is we had these requirements. We said, OK, we want to keep all the events, and we want them to be accessible like really fast. We want to have rapid ingestion. We want it to be in a very low footprint and keep it for a long time and have batch analytics on it and be backward compatible, like everything. So we said, OK, the best way to do that was to take this rapid ingestion, as I said, with Parquet Spark streaming. We've implemented our own Blum filters. Anyone knows of Blum filters here? Yeah, OK. So this is, OK, so I'll explain. But it's widely used. It's a hash function that allows you to keep stuff in like blocks. And you can know for each block if the information is possibly there. It will not miss a block, but maybe it will recommend you of blocks that the information is not there, and you will have to scan through them. But it's a really good way to narrow down our searches. So the interactive queries, again, with this Blum filter indexing mechanism, which is, again, very lean, like 0.5% of the data is in a Blum filter and not like sometimes when you index, you double the storage just for indexing. Blum filters and smart partitioning of the data that I will mention later is a way to have interactive queries. Low footprint, again, when having Parquet and when having low indexing overhead and partitioning, we get a low footprint. Partitioning eventually derives better compression. I mean, compression is everything. Let's start from that. Compression gives you a low footprint, good performance, and a good compression, so naturally, when you partition the data. So it's very important for this kind of system. Again, compression is good for a long retention. Batch analytics, well, choosing Parquet and Spark SQL, Spark ML, we can run everything on that. And it's backward compatible. We have Spark Thrift Server. So all our JDBC interfaces that we had for the system from to our previous data store, it's all there. So we had like minimum change to our system. So the way that it works, I'm just going to breeze through that. So we'll have a table for the indexes. That means information is put in blocks, like 1 million records per block, serially. And then for each blocks, we have the Blum filters for that block and the time range. So if I have like a query on that filter, and that block returns true for all the filters, I will get only the blocks that first, for instance, match our time range, then only the blocks that match our filters, and only then we will run a query that has the block IDs that we're looking for, and this is a lot less data. This is something that is used in databases. There are some file formats that also implement it, like ORC, but still, we wanted to have our own implementation of it. We have word match in that. We have all sorts of optimizations that we did, and we like the control when we have this mechanism. And also, we partition the data. So this is just an example. Every block ID, besides the timestamp, we also have like a client IP hash, because we know that most of the queries will have a client IP. And that really accelerates the query when I have like 10 buckets of client IPs. So I will look only on 10% of the data when I query for a certain client IP. And if not that, we did another really nice thing that I like. We have like the certificate common name. So we took the Alexa top 50, and we said, OK, all of these, put it in one block, and the rest partition in another 9. So if I'm looking for someone surfing to Google or Facebook, I don't care about that. It's like a lot of the data is there, and usually it's not interesting. I'm usually interested in someone performing SSL connections, initiating SSL connections to somewhere else, somewhere interesting. So results are pretty good for that. I mean, if we have like tens of thousands of blocks per day, Blum filter will narrow it down like to 0.5% of those, and query time really reduces to a few seconds. And this smart partitioning allows us both to get less data for a query, but also it compresses much better. So it multiplied our search by like 10 times just with this nice partitioning. Of course, it depends on understanding your customer, understanding the queries, and understanding that in some cases, the customer will ask something that is not partitioned by, but it's OK. It means the customer will wait a little more. But if we cover like Pareto, 80% of the queries, we're in a good position. So just a bit about to summarize the pipeline. I love those slides with the big data pipeline because there's a simple flow to that. You have the Kafka sending all the events in. We have Spark streaming for enrichments, correlations, aggregations, indexing. We persist everything to HDFS or entities or events. We have batch correlations and aggregations that run with Airflow. And we query with the Spark Thrift server. And then we download all the results. Like you have 500,000 results. So we put it in Elasticsearch. But it doesn't matter the exact database. It's just a staging DB for like, let's say I waited for 30 seconds for a response, but now when I facet the data or aggregate, so it's immediate in that staging DB. And this is the nice part. Everything is in Parquet, HDFS. So finally, a thing that we couldn't do until I don't know, last 2 years, we can run actual analytics on that are not part of the system. They're either analytics that our data scientists run or the customers. We have a few customers that insist to have their own data scientists on the data. Of course, it's more complex to manage that, to govern that, but we allow that. So just to summarize this story, what exactly is the research to production process that we have? And this is the thing that I think I like the most in this new approach. So we talked about our operator and the manager and analytics and DevOps, but actually what is the playground? I mean, this is the whole theme of this talk. So our data scientists will having, for instance, Zeppelin, Python, running like on Spark, either her own Spark cluster or in our deployment Spark cluster over HDFS. Everything is there. Everything is available. And she can train models and test their new detections. And the way that it works is that you will have an operator usually working on the system, seeing something interesting, and then moving it like to an analyst and say, listen, this group of alerts, something interesting is going on. Can you please check it or analyze it? And this is like a very usual flow of cyber security center. But sometimes it's not enough. Sometimes we see something suspicious or a lot of garbage for the other matter, or we just don't know if these are garbage alerts or real alerts. And this will be forwarded to either a data scientist on site or our data scientist. It depends, again, on the solution. But usually what happens, and especially in these cases of like it's called zero-day attacks or new exploits, or so in these cases, maybe this data scientist will find a new pattern, and that happens a lot. I mean, this CNC example that I did is a classic one. Let's say we had like a few examples of a command and control connection, and then we found another one that was not detected in our system. So now the model will be enhanced and will be moved back to our DevOps, either to be part of our streaming or part of our batch analytics that run on the system, which will generate new alerts. So still, this is not something that either the customer or we do like on the fly. It's really hard, as you probably know, to add like new stuff to Spark, like a Spark cluster without any real cycle of quality and resource allocation. So we have allocated resources for this research, but if we want to put something that will be a standard thing in production, especially in streaming, by the way, it has to go through this DevOps phase, and it will be integrated in the next version as a part of the system. So we did this a few times, and I have to say that what I'm proud the most, that the first cycle took us many months, and it was painful. But now it's getting faster and faster, and in a matter of weeks, we can complete a cycle. And this is the thing that we put a lot of effort into, this research to production, because once you deploy the system, if you don't follow the network, if you're not following what's going on, the system is not something that you install once and will live forever. You have to maintain and monitor the events, and our really sophisticated customers, they understand that, and they want their people to also to be a part of this process. This is something that we get more and more required from us. So just to summarize, this was a really high-level description, but I hope I managed to explain some of it, of the process that we had. It's been a real growth journey for from a few a handful of programmers to many dozens that are working on these systems, just on this part of the big data. It's all thanks, well, as we all know, democratization of big data. It enabled us to have a rapid R&D that we would never expect. It's all in a single platform. The performance is high, and it manages millions of records over trillions when stored, but millions per second in the largest deployment. And it's also very elastic. We have solutions that are 3 master servers and 3 workers on VMs, very, very low throughput. And the same code runs in our largest one, is a 200 server cluster. So we have this elasticity and a way to manage everything under one code base, even though you have to manage the DevOps efforts to match to the different environments. And eventually, of course, the research to production cycle, which is the most important thing for me anyway. Okay, that's it. Thank you. And I'll be happy to answer any question. Yes.
You mentioned the typical Hadoop technologies like Spark, HDFS. Are there any other technologies that are emerging right now that you are looking into, or are you fine with the setup right now? Are there any big ones?
Yeah, well, that's an excellent question. First of all, that's why we come to these conferences, because we don't want to be left behind. And now we're in a stage that if I come to my manager and say, listen, I want to add a new technology, he would throw me out the window. He said, no, please don't. Okay, but we have people looking at Flink, and we have well, you know, the thing is that Spark is so strong right now that whatever other technology does, it just collects and keeps up. So we're just following the Spark roadmap for now, and we really love Kafka and what they offer. And Kafka also have awesome stuff coming right now out, and we think, okay, but we have the Spark job, but we can do it in Kafka streams, we can do it in KSQL, and you know, but these are like, we try to stabilize now and say, okay, let's make it work. But I'm positive that if, you know, we come back here 2 years from now, we say, what, you're using Spark? No, I'm hurrying now. But, you know, you know, because, you know, MapReduce, you know, when I learned MapReduce, I said, wow, we have to do this MapReduce jobs. And now it's like no, I don't want to say a joke, but nobody would, you know, nobody would tell me, okay, you're right. So we know that this is a fast evaluating, there's a fast evolution here. But the main things, our main goal now is moving to containers. This is like, and this is coupled with our understanding that cloud is inevitable, and we want to move there, and we need to convince our customers to move there as well. So it's both the cloud deployment, and it comes with this Spark and Kafka and Kubernetes and more of the other aspects of our system to be in containers. So this is like the main roadmap for now. Yeah. Any other question? Well, anyway, I'll be here, so you're all welcome to talk to me or contact me, and follow or LinkedIn or whatever. I'll be happy to. Okay, thank you.